So, in the last lecture we talked about this ice rafted debris which was brought in by the large ice sheet in the over Canada called the Laurentide ice sheet, which broke off as it came near the edge, and along with it brought all the rocks and sediments from land into the ocean. These fell into the deep ocean and collected there, and by collecting these sediments from the ocean floor, marine ice core, marine ocean core as they call it, we are able to understand what happened in the past. So, both ice cores which I discussed earlier and this marine sediment core are two important sources of information about the past climate of the earth. Without that, we could not have understood what happened in the past in the case of earth's climate changes. Now, I talked also about the Atlantic meridional overturning circulation, that it is an important part of the of the ocean's circulation system, which brings heat from the tropics to the poles. If you recall, tropics gain heat from the sun, while the polar region lose heat because there is not much solar energy absorbed. So, this transport of heat from the tropics to the polar region provides the balance that is needed to maintain the temperature in a more uniform fashion. Okay. So, the reason why we are going to spend some time talking about AMOC is because of the prediction that increasing greenhouse gases like carbon dioxide and methane will weaken this circulation and lead to large changes in Earth's climate. And the fear is that this circulation pattern, which is bringing heat from the tropics to the polar regions, which is driven by variation density between the tropics and the poles, might suddenly stop because of the increase in CO2, and if it stops, it will cause a major catastrophe. Okay? Because the Earth's climate has been reasonably uniform for a long period, and we have got used to it, and our agriculture is based on the assumption that the Earth's climate will not change rapidly. But if the circulation stops, it will result in a very, very rapid change in Earth's climate, which will make both the tropics and the mid latitudes not livable. So, it is a very important issue which is being debated, and I will spend some time about it later when I talk about future climate. We come once more to the important Younger Dryas cold event, which occurred around 13,000 years ago, just after the boiling alloy event. Okay. And you notice that this graph shows both temperature and the ice accumulation. You notice that temperature is high, ice accumulation is more. When the temperature drops, the ice also drops. Now, some of you may be surprised. You might think when temperatures are high, there will be less ice. Yes, ice will melt when temperature is high, but remember, for ice to form or snow to form in the atmosphere and fall as snow and ice, you need moisture. And the amount of moisture in the atmosphere is controlled by temperature. If the temperature is too low, like it is in Greenland around minus 60 degrees centigrade, there will hardly be any moisture in the atmosphere. If there is no moisture, there will be not much snowfall. But once the temperature goes up by 10 to 15 degrees, snowfall will start increasing and ice will build up. So, you must remember that for snow and ice fall, the temperature has to be below 0, but cannot be too low. The temperature is too low, there will be hardly any snowfall or ice. For example, today Antarctica is very cold. That is, there are parts of Antarctica where there has been no snowfall for the past 2 million years. Imagine this. For 2 million years, there are parts of Antarctica which had no snowfall. Okay? So that shows that during periods of very cold climate, ice cannot accumulate. Ice can accumulate only when the temperature below 0, but not too low, so that snowfall can occur and ice can build up. So you can see clearly difference between minus 60 and minus 50 in Greenland, and also minus 60 and minus 40. So from minus 60 to minus 40, the ice accumulation has gone from almost 0.05 centimeter, 0.05 meter of ice accumulation to 0.25, 5 times. So when the temperature goes up by 20 degrees, ice accumulation goes up 5 times. So there is a huge amplification of the hydrological cycle. Now we talk about ocean circulation, how it starts with the tropics and goes to the poles. We talked about how it moves vertically, but it is very important to understand that a lot of horizontal motion in the ocean. Okay? If you take any water parcel and follow it physically, this water parcel will circle horizontally for a long period, couple of decades, before it moves north and finally sinks near Greenland into deep ocean. And once it goes deep inside, it will come back to the surface again after hundreds of years. Okay? So this should be understood, that ocean has a lot of horizontal motion called gyres and a lot of vertical motion due to density gradient. Okay? Now the upper 25 to 100 meters of the ocean is well mixed by winds and waves. Winds blow the ocean and churn it. The churning occurs over a thickness of 25 to 100 meters. Okay? Once you go below this mixed layer, temperature decreases rapidly, and this is called the main thermocline, where temperature decreases from the top of the mixed layer all the way to the bottom. Then below that there is a layer of almost constant temperature. Now here is a nice depiction of the ocean circulation by NASA, who provide very good visualization techniques. So let us follow this clearly. So the water, which is warm and less salty over the tip of Africa, moves northwards, goes past South America, goes past America, turns sharply, and then moves towards Greenland. Notice that this circulation is not anywhere touching the coast of United States. The reason why I call the attention to this is that another circulation system near North America called the Gulf Stream. The Gulf Stream is different from this circulation because the Gulf Stream is driven by winds. Winds on top of the ocean drive a powerful circulation system, okay, but mostly near the land. Once you come to deep ocean, the major driving force is the density difference between warm, less salty water and cold, salty water. Okay? So this AMOC also, although it goes quite close to USA, it is different from Gulf Stream and it moves towards Greenland. Then it cools, loses a lot of hot water, becomes cold and hence dense, and falls into the deep ocean, blue color here, and the deep ocean water moves slowly to South America, and then from South America it moves horizontally across the just in front of the Antarctic Ocean, and one stream moves towards Africa, and then it gains enough heat and temperature goes up, and then it comes over in the southern Indian Ocean and then joins the stream which comes from going over the Pacific Ocean. So what you must realize is that ocean has both horizontal and vertical circulation, and our concern right now is in a horizontal circulation, because that's what transports maximum amount of heat from the tropics to the mid latitudes. Okay. Now I want you to study this nice circulation animation by NASA, so that you understand the complex horizontal and vertical motion that goes on in the ocean, which helps to transport heat all over the world. Okay. Now I want to differentiate this circulation from the Gulf Stream, which is driven mainly by winds, which occurs very close to the coast of Florida and moves quite close to the ocean in North America, but soon it comes out, moves to the east and has series of vortices which break up and transport heat all the way to the European region. So the Gulf Stream along with the AMOC are the two major factors which contribute heat to the land region, both in USA as well as Europe. So this Gulf Stream is very important to bring in much more equitable climate to America and Europe, and this is different from AMOC. AMOC is further to the east, is drawn by mainly by thermo-Haaland circulation. Now I am saying this because many media outlets confuse between the Gulf Stream and the AMOC in the Pacific Ocean. Now here is an animation. I want you to watch the movement of the Earth, again given by NASA. You can see in white the surface circulation coming from the coast of Africa and going up towards Greenland. There it sinks. At the bottom you see blue colored arrows coming southwards, and this animation shows going deep inside the bottom of the ocean as the ocean water becomes denser and falls into the deep ocean. And now we will watch as this animation occurs how the deep ocean water will take this heat all the way back to Antarctica. Okay. So just watch this animation, which is showing nicely both the vertical motion and the horizontal motion. You can see now the return flow at the bottom, the blue color, going down at the bottom of the ocean, all the way bottom of the ocean in the South American region, finally reaching the Antarctic region, and then slowly moving up, and in the tropics it comes up as warm, less salty water, and then moves again to the Atlantic Ocean. So this complex ocean pattern, which involves both horizontal motion and vertical motion, has a huge impact on Earth's climate because it transports a lot of heat. Okay. So if this Atlantic meridional ocean circulation suddenly slows down or stops, the Earth's climate will change suddenly. Okay. So, that is why we want to study this particular ocean circulation with great interest. Okay. So, now we move on to the next slide. Now, let us look at the slide again. The animation works now at a bigger scale. So, you see warm water, white arrow showing warm water surface going towards the Greenland. At Greenland, it goes down, and it goes down as cold salty water. Then it moves deep in the bottom of the ocean on the way back to the Antarctic, and you see this circulation at the bottom of the ocean, cold salty water, and it moves now towards Antarctica, past South America and towards Antarctica. In the meantime, the warm less salty water is coming from Africa. Okay. So, this whole pattern, which is a complex S-shaped curve, takes hundreds of years to complete. So, the water which came down near Greenland goes all the way Antarctica, goes around Antarctica, then comes up around the tropics up, and it picks up heat, becomes at a high temperature, has a lower density, and it moves to So, here is a details of the current near Greenland. Okay. The reason I am showing you this is to point out the complexity of the local currents. Okay. Although we will make a simple description of this Atlantic meridional ocean circulation, in reality it has got many other currents also, and they all interact with Earth's climate. So, although we will make a simple description so that you can understand the important role played by the ocean current, but you must remember that close to Greenland there are many other currents also flowing around. Okay. They have been given various names, and those also alter the way things behave around Greenland. Okay. So, in order to simulate these flow of the ocean, you need a complex ocean atmosphere model. You cannot do it very simple, although we use simple models to understand the complex model. The complex model has to incorporate all these details of the currents. That is why when I compare different models, usually they do not agree. They do not agree because all of them do not take into account all the complexities of the ocean circulation near this region. Okay. Near Greenland, Iceland and England, these currents are very complicated, and to simulate them accurately you need a lot of highly accurate, high resolution ocean model. Okay. Here is another picture showing all these currents and their names. You do not have to remember it, just for your information. There is the East Greenland current, West Greenland current, Labrador current, Canary current, and all these play a role in transporting the heat and salt and in controlling the amount of heat transported from the tropics to the polar regions. Now, let us go back to the data from the ice core. The ice core data shows that the Greenland ice core shows a sharp temperature drop during the Younger Dryas event, which shows a sharp drop in ice accumulation, shows also a sharp drop in temperature in the region called Cariaco, which is near Venezuela, that is near the equator. Okay. So, even in the equator you see a fairly sharp drop of around, I would say, 3 degrees temperature. Here is more like 10 degrees, here is around 3 degrees. But the surprising part is when you go to Antarctica, there the temperature goes up. Okay. So, this is an unusual feature. During the Younger Dryas, when the temperature drops suddenly in the northern hemisphere, temperature in the southern hemisphere actually went up. So, this was a great surprise when it was first discovered, and this is called a seesaw. Seesaw means change which was opposite in the two hemispheres. So, in the one hemisphere temperature goes up, in the hemisphere temperature goes down. So, this came as a surprise, and this occurred because when the AMOC either slowed down or stopped, it did not transport heat from the southern hemisphere to the northern hemisphere. Hence, the southern hemisphere started warming up because heat remained there. And since this heat did not reach the northern hemisphere became colder. So, you notice that the changes in the ocean current AMOC has a opposite impact in the southern hemisphere and the northern hemisphere. If AMOC stops, it does not transport heat to northern hemisphere starts cooling, while southern hemisphere retains the heat, and so it goes up. Okay. So, keep this in mind. When this ocean current is accelerating, it will transport heat, as it happened in the case of Bolling Aneroid. During this period, the current was strong, it transported heat and it cooled the Antarctic region. When the ocean current stopped, the Antarctic warmed and the northern hemisphere cooled. So, this is a very important thing to understand, how northern and southern hemisphere go in the opposite direction because of the changes in the Atlantic Meridional Ocean current. Okay. This is a point you must remember clearly. Now, past changes in AMOC show that AMOC is not stable. It has periods of low and high transport of heat, and we are concerned about it because the anthropogenic emission of carbon dioxide accumulated in the atmosphere, and this will cause Greenland ice sheet to melt, and this may lead to the weakening of the AMOC with an important impact on the climate of the earth. Okay. And so, this is a current concern of all scientists working in climate science, to understand what controls AMOC and how it changes the global climate. Now, to understand this, we need climate models of various levels of complexity. We need simple energy balance models, which we have used in this course earlier to understand the global mean temperature, but they are not enough. We need information about North Pole and South Pole. So, we have to go to what are called EMICs, Earth Systems Model of Intermediate Complexity. Okay. So, these are more complex than EBMs, but less complex than GCMs, Global Climate Model. Okay. EBM simulate temperature accurately, but if you want to understand circulation, you need to bring in EMIC, okay, which are more complex than EBM, but on the computer they run more slowly, but they are faster than GCMs, Global Climate Models. Okay. So, we need all the three. We need EBM because they are simple and makes us understand how the energy is transported. We need EMIC, which has some circulation features as well as energy balance to tell us what will happen over a period of couple of 100 years. But finally, we also need GCMs because we saw that the ocean current near Greenland was very complicated. There are lots of small currents there in addition to the main current AMOC. So, to resolve all that, you need a coupled ocean atmospheric general circulation model. So, I hope I have convinced you that we need all the three kinds of models, simple, intermediate and complex, to understand Earth's climate. Okay? So, we will use all of them to understand the Younger-Dryas event and the Bolling-Aileroid. Now, I want to highlight this because it is not enough to believe in the prediction of the complex model. The complex model is so complex that you should not trust it totally. You must make sure that when the model predicts something, you understand the prediction. So, I want to quote the famous statement by Nobel laureate Shigoro Manabe, who said, "Prediction of climate change without accompanying understanding of it is no better than prediction of a fortune teller." This is a very important statement because today all of you are going to see more and more use of computers, use of machine learning, artificial intelligence. All these are essentially black boxes. Okay? They will give you a prediction and they will be accurate most of the time because they are trained well, but you cannot trust it totally. You have to understand what these complex models predict from basic physical principles. If you do not understand it, you cannot be sure that the complex model got the result correctly. Okay? Because when you run a complex model, there could be some solutions which are not physically realistic. Okay? Because as you saw earlier and I will repeat later, that complex models have various approximations. Because all the complex models represent the Earth much better than simple EBM and EMICs, they still have limitations. Okay? Because they cannot reproduce Earth complex climate system at all scales. There are things happening over a kilometer scale which is not resolved by a climate model. So, whenever you get an output climate model, you must make sure that you understand it completely. Okay? That is why we need a combination of good observation, complex models and simple models. Okay? Now, why do we need the models? Because proxy data, although they are amazing, not always reliable. One of the limitations of the proxy data is you have to convert the proxy data to either temperature or circulation or rainfall. Okay? While doing that, you make some assumption. Those assumptions based on present climate may not be true in the past climate. That problem occurs. Okay? That has been partly solved by proxy data. Proxy data gives you more confidence because proxy data has much more different proxies. So, all of them cannot give you the same answer by accident. So, you trust proxy data more when you have multi-proxy data. Okay? And so, you want to combine that with climate model. So, I am going to now in the next lecture talk about the changes that have occurred in the last 20,000 years and how they have been obtained from observation, that is proxy data, and how well both simple and complex model reproduce that change. So, once you understood these changes occurring in the Earth's climate through simple model, complex model and proxy data, we are in a better position. Okay? One point I want to highlight, One of the weaknesses of proxy data is that we don't know exactly when that data occurred, because we have to infer the time in which that event occurred by indirect means, by assuming the time during which this deposit occurred. Their errors can be easily 100,000 years error can be there. Okay. And if you are not sure of the deposit rate, you have to use radioactive decay method to infer the time, and there are errors in all these methods. So, proxy data has two errors. One, how you convert the proxy data like tree ring to temperature. Secondly, how do you identify the time exactly? Both these pose problems, and that is why proxy data has been supported by Clement bottle. So, I will continue this discussion in the next lecture.